But the last question on problem set 5, that's like half the problem set. So, but we haven't even started on that one yet. Anyway, so on the next problem set though, there's a question with a trace. And traces are really important, not so much for the types of like spin up, spin down problems that you're doing right now. It doesn't mean much, but on other problems they mean a lot. So now I just wanted to point out that when you transform a basis, the traces and so notice that what I've done here is remember that. So this is kind of important. So you kind of try your best to remember this. That sorry, and I'm going to use the book's way, which I don't like very much. So the thing to remember is that the bra is what increases on the left, and the ket is on the right. Now I gotta think. Right, okay. Let's have to think about it for a second. Okay, a double prime, and then okay. So anyway, just you're going to have a couple of these. So just kind of try your best to remember that the bras are what increase on the column, and the kets are the rows. That's kind of useful. All right. So and of course the trace is the sum of the diagonal elements. And when we get into some other type of operators, it's going to have a physical meaning. Right now, it's just like. It's like a characterization that doesn't matter, which is actually a very good way to describe it for now. But what the book is trying to get you used to is just, they're just trying to make sure you know what it is. So let me do 2 resolutions of the identity, and I'm using the book's crazy dashes. Again, the book is really bad about the way they do with dashes, and I find it crazy, and I've tried to be more careful in the book, but anyway. Now again, what's good about this, I just want to remind you about this one last time, and also a little bit of practice with, what am I doing? Resolutions of the identity, and you can slip them in anywhere. So that's what I wanted to mostly, that's the reason I'm doing this, is to remind you of that. So outer product, remember that's technically an outer product. So I've slipped one in here, and I'm going to slip the other one in the other side. Remember that numbers, including partials, can go anywhere. They can be inside an inner product or whatnot. Okay, and wait a minute, what the hell am I, what's wrong with me? That's not an outer product, there we go. Okay, now that I've done this, these are numbers, right? Inner products are numbers, and they can be manipulated. And anyway, again, I want to do this just to remind you, and also have some practice with resolutions of the identity. And then I've got some practice, with what we did with position operators and position resolution of the identity. Sorry, God, what's wrong with me? I gotta warm up, I guess. Okay, what I've done is I'm bringing this over here, and this is one of the best examples of resolutions of the identity being really essential for doing proofs. I just can't imagine how painful this would be. If I didn't do this with Dirac notation. Okay. Sum of A, and I've got an outer product. All right, so that's 1. So I'm going to cross it out, not as a 0, but as a 1. Okay, now I've got double sum, and what I'm going to find is a Kronecker delta right here. So these parts collapse together. And here I've got a Kronecker delta. Recall that you can, it's up to you whether you want to make all the B primes B double prime, or all the B double primes B prime. I think there is some kind of formal rule to this, but I don't know what it is, and I know for a fact it doesn't matter. So I'm choosing to make all the B double primes primed. That one right there. So there you go. Notice that this is a trace. So this is a sum of diagonal. There's a matrix representation of this operator. This is the matrix representation of this operator in the B basis set. I've summed the diagonal elements, and the whole time it's been equal to this. So this whole thing is the matrix representation of the operator in the A basis set. That's the sum of diagonals. And at every step of the way, it has been equal to, equal to here, which is the sum of diagonals in the B representation. So what it means, so let me just write that down just as the last step so that you so one of the problems I think comes with proofs is that you tend to forget that you've been, equating every step is equal to the last step, the next step is equal to the last step, and on and on and on. And of course the point is have the last step equal to the first step. And so the point of this is that the trace of the matrix representation of an operator is invariant. So I'm going to use highfalutin words here, invariant to representation. And again, my spelling is bad, so is my writing, I don't know why. Anyway, so a little reminder of that. Okay, now let me do a little reminder of position operators. Oh, not position operators, position resolution of the identities. So I hope you remember that. Okay, so I'm on another subject, continuous variables, just like this in our previous example was the number 1. Now that's this when it comes to something that is continuous versus discrete. Up, down, there's only 2 of them, whereas between 0 to 1 nanometer, there's an infinite number of spots between 0 and 1 nanometer. And they're all equal. They're all equal to 1. Right? So that's how you resolve an identity. And remember, this was really important. I have to admit that I've been kind of fibbing on something. I have been telling you that this was like a wave function like sine kx, and that's not really quite right. So here I'll draw a little Gaussian. That's a nice little wave function. This is not the wave function. It's a part of the wave function. So when you see an x, a bra or ket, don't think of it as the x-axis, think of it as a point on the x-axis. So when you're working with this needs to be defined as 1. So let's say that this is position in nanometers, that's reasonable. Here's the value of the wave function at position 1. If this x is the 1.0 nanometer x, then this is that value right there. It could have been the 5.0 position. Technically, that's a bra. It could have been 5.0. Whatever. And then the value of that inner product is whatever that is, whatever that is. Right. So again, it is. I wanted to remind you. We did a lot with sine pi x over L. And then we went into direct notation, and now we're connecting the two. Now, if you actually want to represent the wave function, what you would would be better is not so much this, which is what I described. That's actually this. This is a better way to think of the full wave function, because remember, integrals are just sums of things that are continuous, not discrete. Okay. Spin up, spin down is discrete. X and P are continuous. So this is actually a better representation of the full wave function, and that's just the point of the wave function. So that's important for when I do some of these steps. Okay, so anyway, I'm still trying to remind you. Let me do a little bit with resolutions of the identity. Okay, that's 1. And, sorry, where am I at? I'm not in the right place of my nose. Sorry, let me complicate it a bit. Let me do a basis set. So what I'm going to do is, sorry about that. Okay, so notice what I'm doing here is I'm taking a projection of alpha, our always constant unknown state, into a basis, and let me now expand that out so that you recall again the number of states. Hopefully you recall what an absolute value squared is. It means you've got a complex conjugate, and here's the non-complex conjugate. Complex conjugate times the whatever. Now I can see that I've got a resolution of the identity. I've got a resolution of the identity, and so I can get rid of it. And that's how I know that this sums to 1. So again, this is actually like the absolute value of when I represent a state like as a column matrix. These are the numbers in the column matrix. This is the 1 over the square root of 2 plus 1 over the square root of 2 minus state, which represents an SX plus state. It's an absolute value. Anyway, all right, so we've done stuff with that. Okay, now let's, if we now apply that to our position operators, what is this equal to? And I need to have a partial. Okay, so the sum is now integral, and I've got the alpha state x, and that's a complex conjugate of this. And I can see that I've got a resolution of the identity. But now clearly, again, I've got a resolution of the identity, and so it's just going to turn into the inner product of alpha, assuming it's normalized. So instead, let me do this. Let me point out that this is actually the alpha state. Again, I want to connect to your undergrad. Well, we always go over an undergrad. The normalization requires that the complex conjugate of a wave function times a wave function is 1, right? So that's something you covered early on into undergrad. So anyway, again, I hope you should remember that from your undergrad, and I'm just doing a little practice with position resolution to the identity, which we're going to do a lot more with these today. They're really awesome. The more you do this, it gets real easy. And like I've said a billion times, all this quantum stuff is really a matter of practice, because I can't really, I just don't know that I can make it easy, but like all things, a lot of practice. You're going to add resolutions to the identity just like nothing, and it'll always just lead you straight to the answer within 2 or 3 steps. You have a homework problem where you have to take 2 operators and their adjoint, and it ends up like, what's the adjoint of AB? And it's just BA, and you use a resolution of the identity to solve that, by the way. That's one of the harder problems. It can be hard, but if you use a resolution of the identity, it's very easy. Okay, for today, we're going to cover the translation operator. Okay, another example like the projection operator that transform U, what I've been calling U as a projection operator. It takes me from one basis set to the other. Now that's an example of an operator. I don't know how much you maybe have noticed this, but that's an operator that's like what? Right? Now we've had operators like Hamiltonians, momentum, and position that report energies and position and momentum. Right? And those are Hermitian because they're real things. But projection operators, they don't report eigenvalues, they mold things, they turn things around. And for reasons you'll see, it's very useful. Again, that's when we do time-dependent quantum theory. Now this is another one. This operator, it's a real Bismarcker. It's not reporting eigenvalues. It does something else. And what it does is, let me show you. You're going to apply some value to it, to a state. And what you're going to end up with is that state plus offset. It's basically an offset. Okay, so what I'm doing here is, let me go back to that wave function I drew a little while ago. What you're doing is, you're saying, okay, I'm right here. Let's say you're at the top. What this does, it ultimately queries the wave function at some delta displacement. So I'm assuming that you know what your wave function here is, and what it does is this translation operator, it says, okay, well tell me what's immediately to the right, or left if delta is negative. Now, hopefully you look at that and say, well, who cares? And the answer is no one. This is another ridiculous operator. The point of it is to get you used to a very different operator, which is the time translation operator, or the time operator. The translation operator and the time operator are almost identical. This operator, no one cares about, but it's good warm-up for time, because time matters. This is BS, just to let you know. But we're going to spend 2 or 3 days on it.
And just position, right?
Huh?
Just position change, not the...
I just changed the position. Yeah.
Not any time dependent.
No, it will be identical to time. And but it's just harder to understand. This, I mean, look, yeah, I just moved this wave function over. I mean, my cat probably understands that, you know, knock the toy over. All right, but when it comes to time, I want you to get used to this because everything's going to work out mathematically the same. So at least you're not going to get stuck on like the operators. You're going to get stuck on like, what does that mean? I don't want you to get stuck on the math and what does it mean at the same time, because then you're kind of screwed.
When time comes, we have 2 operators, right? Position and time. So.
No, not really. Well, you'll see. Well, what you do, you're probably talking about something I hinted to a minute ago. What you're going to do is change the position operator to be the time-dependent position operator. And you're going to do that versus saying you're going to let the states not evolve in time, you're going to let the operators change in time. Or you can let x be x, position operator, and let the states evolve in time. It's just that it's usually not done that way. And when we get to it, you'll see why. It's going to be like a little bit easier. So anyway, all right, so this is kind of a ridiculous problem. Like, you know, if I'm here, I want to go there. Why? Because again, instead of position, it'll be time in about 2 weeks, and that's really a good thing. Okay, so the way it works is, okay, I'm here. What I'm going to do is I'm going to do a resolution of the identity. Well, here I'll apply it to state alpha, and because at that point now I'm talking about a real wave function. Remember that the wave functions of position are actually delta functions. This is my Gaussian, right? So that's what that alpha is. Okay, resolution of the identity. And I'll try to be careful with these dashes. Now remember I told you the book goes crazy with dashes. I think that all the dashes are accounted for correctly, but it just gets confusing because 2 dashes, 3 dashes, what dash corresponds to what resolution. Anyway, it gets confusing. Okay, so now, but the translation operator then works on that ket, so I better make it a ket instead of whatever the hell I just drew. Okay, so there you go. I just projected this state, so that's like here, and I just moved it over. That's how it. So remember, you think of this as like the full wave function. So what I've done is I just literally pushed it over slightly. And again, why? Because I can. And you can do this, it's meaningful, and it's great practice for what's coming. Okay. Now, in terms of what is the translation operator, you figure it out using 4 properties, which when goes 4 is identical to time, to the time operator, the time translation operator. Okay, if this is true, then you need to have this true. Remember, this is called norm preserving. And a lot of these like ridiculous operators that don't really do things except like turn things into other things, We have an operator that we're going to cover in about a month that its job is to turn a ground state to an excited state. And it's called a ladder operator. Those are really important. I hear ladder operators in class all the time. Okay, now again, remember that this is norm conserving. It means that the state still integrates to 1, which damn it, ought to, right? Ever since undergrad, we're like, this needs to be normalized. All right, so that means that this is equal to 1. And that means so it's equal to 1. And the word for that is that the operator is unitary. And that's why when I was doing those change of basis operators, that's why I used U for those operators. It stands for unitary. That was just my introduction to unitary operators. That's why I called it U. Okay, so there's that. This is an easy one. There's 2 more. And then I'm going to propose a structure for the operator, and then we'll show that it satisfies these 4 conditions. And so this one's kind of easy. If you translate something twice, it's equal to, there you go. So that one's kind of hard. Let's see. Okay, now this one is actually the same as number 1, which is really nutty. You'll see that in just 1 second. Let's see. So this goes backward, right? Now, if you look here, if this goes forward, this has got to go backward so that you still end up with alpha alpha. All right, you follow me here? This drives you forward, so this better drive you backward to the original state, so that way I still have the alpha bra and the alpha ket, which is still 1. Right, so if this is going to be, if this ultimately doesn't do anything because it's the number 1, then this thing kind of needs to undo what that does. Now, if this drives you forward, then that drives you backward. So what that means is that this has got to be equal to the inverse of delta, and that also means that it's equal to the transpose of delta. Now, I've actually covered this part before. Maybe you don't, hopefully you remember. If this is 1, then the transpose has got to be 1 over. Anyway, again, my handwriting is not great today for some reason. Okay, there you go. That's easy. It doesn't come up too much. 3 and 1. 3 and 1, those are actually the exact same thing. It's neat that they don't look that way, but they are. Okay, then if delta goes to 0, then the operator better go to 1. Right? Not therefore goes to 1. And that makes sense. Okay, now I have these 4 properties, and now what you propose. Oh, and you know what? I just realized I was doing this. I need to have little hats, right? I need to have little hats on everything. And that's important because I need to put a little hat on this K, and K is not known. And the book uses a little dash. I don't know why they put dash on everything. You don't need to. Anyway, okay, so sorry, I should have had a little little hats. Everything's an operator has a little hat. That way it feels special. Okay, I'm proposing that this will satisfy the 4 conditions. What I don't know is what K is. Slight problem there. But the overall structure, so again, I'm proposing an architecture, but it's not defined what K is. So anyway, let me point out, okay, so 4. So let's review. Let's see, is 4 satisfied? So now this is something that makes me angry. remember that partials are 1 over infinity, but not 0. Right? Partials have units. They're infinitely small. Infinitely small is, by definition, 1 over infinity, but it's not 0. What the hell? You can't have that. You can't have that both simultaneously be true. But if partials were 0, calculus wouldn't exist. Yeah, that's always made me super angry. And maybe aliens have figured out, I mean, I know that can't be true, but anyway, but calculus also works, so maybe aliens figured that out. Okay, if the delta, if the partial of x goes to 0, then of course goes to 1, right? Because that's 0. So that, that one's stupid, right? Okay, so let's look at 3 and 1 simultaneously. So this is technically, let's review condition 1. Actually, what is condition 1? I already forgot. Okay, so it turns out that, okay, now this is another thing that really pisses me off. Okay, so let's write the transpose. Instead of minus, it's going to be plus. Okay, so this is this is the adjoint. God, have I been saying that right? Sorry, inverse adjoint, they're the same thing, my bad. Right, the adjoint, this is the operator that's the adjoint of the operator. It turns out the adjoint of the operator is just the inverse. Whereas remember, Hermitian operators, the operator and the adjoint of the operator are identical. Okay, anyway, little hat. Okay, now as I told you, this is one of those things I really hate when this happens. It's always pissing me off. Okay, this is 1 plus k squared delta x prime squared. Yeah, because the cross term goes away. A plus b times a minus b is just a squared plus b squared, right? So a squared plus b squared.
It's minus.
No, it's minus I squared.
Yeah,
minus I squared. Yeah. Remember, it's like the absolute value, right? Okay, now get this. Partials are 1 over infinity, but not 0. However, if you square it, it's considered at that point, then it's small enough that you just discount it. One over infinity is not 0, it's close to 0. Unless you square it, then it's 0. And if that sounds like, wait, that doesn't sound right. Right, it doesn't sound right, and it drives me nuts. But there's so many proofs when you have a partial and you can square the partial, you just get rid of it. Now I admit, 1 over infinity times 1 over infinity is definitely a really much smaller number than 1 over infinity. But if you can't say that the 1 over infinity is already 0, then I don't quite know why that's allowed too. Anyway, it's just a little thing that always curious. Huh?
So for the third one, is operator is an admission or an unit operator, right? Because the inverse is equal to the adjoint. For the third one, the third rule.
Third one? Yeah?
We are saying the inverse is equal to the adjoint, right?
Yeah.
So it must be, is it admission or a unit operator?
What again?
Is it admission operator or a
Emission?
admission?
Hermitian. No, it is absolutely not Hermitian. Absolutely not. Now, for one, the definition of a Hermitian operator is that the adjoint is equal to the operator, not 1 over the operator. So this is no, this is no. No, I didn't say that up here. That's minus delta. Minus delta, that's plus delta. No. So, like I say, I think I don't quite remember how to do 1 over a complex number in my head, but that is what it is. And regardless, this has to be the adjoint because sorry. All right, for one, this is moving one direction, and this is moving the other direction, right? Because I got a plus delta x, and I got a minus delta x, I got a plus delta x. So at the bare minimum, I'm doing two, aren't I? I'm kind of doing, no, I'm doing one. I know, I'm confused. Really, they all work together. That's the kind of thing that kind of slayed me. I prepped for this, and it kind of is confusing when you write this stuff down, which one of these you're actually solving, because you kind of can see elements of all four of them simultaneously. So to some degree, if that's moving one direction, this is clearly moving the opposite direction, which makes it the adjoint. But it's also, let's see. Okay, let's review number 2. And so what that is, and again, this is another one of these that is going to make my blood boil. And what you end up with here is 1 minus, there is a factor in common, which is ik delta x prime and double prime, and then you end up with a minus k squared cross term, which it's 2 partials, so we now we can say that's 0. Okay, so again, if you translate by delta x prime, then translate by delta x after that, then the operator is basically the same thing. Yeah. Okay, last bit, and I have to kind of run through this kind of quick. In terms of what is K, I didn't put little hats on. I'm missing a little hat. I'm missing a little hat in a couple places. Sorry about that. Remember, K's get little hats. Terribly important. I gotta get back on my textbook. I've written an undergrad thermo textbook, and then I got paid to start a graduate textbook, and I've only done half of it. And that's something I obsessively look over. I make sure that I'm not missing little hats or anything like that. It drives people crazy. Okay. Now the question is, what is the K? What exactly is that? Right. So I've proven the architecture. Now that bothers me. I've proven the overall architecture is okay with sensible properties. So in properties 1 through 4, they just make sense, right? Now I need to know what the K operator is, because I haven't said. Okay, so the trick is to do this. To calculate a commutator. And let's see what that is. That is X. Translation. Oh, and I should have a little hat. God, I keep forgetting the hat for some reason. Minus the translation operator. Okay, how much to that? Now, as in a lot of things, you're stuck. So what you do is you apply a ket. Let's just give it the number 5 to work on. And when you get, let's do, okay, so be careful here. I'm now going to step in 2 different directions. So this is the X operator operating on a ket, which is X plus delta X. Okay, which of course is X plus, these are numbers. Okay, again, break this, I know it's a whole bunch of squiggles and whatnot, but it's really straightforward. And then we'll invert, permute. It's not an inversion, it's a permutation. Okay, I'll permute the operators, and so this thing is going to operate on X prime, and so that's going to spit out a number. A number can just slip past the operator, just like 5 times the derivative. Derivative of 5 times a function is 5 times the derivative. Numbers you don't have to really keep track of them. And it's operating on the X prime state. Okay, and this ends up being x prime. Okay, so you can see what I've done here. And, okay, so what that means is that, remember that the commutator is one minus the other. Okay, so this ends up being, well, I think you can see it here, right? I've got this here, and I'm subtracting this from this, so it's equal to the x prime. This part, this is, this minus that, it's obvious, right? Okay. It may, the thing is, I know it's obvious now, but when you reread your notes, maybe you're going to be a little bit confused. Okay, now I told you that today's lecture is full of BS. Apparently, we have to make this approximation. You have to make this approximation. And that enrages me, because it just does. Okay, next step. Okay, now, do over with the translation operator. Okay, so we have to figure out what k is. And so when you do that, minus, I'm not going to do this, this is really not too hard. What you get is x minus I dx k operator, which we don't know what it is. Okay, so that's this thing, x times, right? Now, the thing that's kind of stupid is then you get this little hats. Wait, sorry, what the hell is wrong with me? X prime. Okay, so what you should have noticed is that I've permuted xk and kx. That's really all I've done. Yeah. Okay, and then this is equal to, now here's the trick. I'm doing this. I know what the result should be. Wait a minute, what the? Yeah, that's, no, I knew something wrong. Sorry, God, sorry. Okay. Now, again, I want to emphasize that I got that from here, and I know I need to finish up, so let me tell you what I do next. The x's have canceled, and now what I'm going to do is I'm going to divide by I dx prime. God, I know this looks awful, doesn't it? Which is equal to minus I, right? Hold on a second.
Minus I.
Yeah, minus I. Let's see here. Hold on. So this is xk minus kx. And this has got to equal minus I. I think I made a mistake in my notes. I have to double check.
That's fine.
So, is this right?
Yeah, because if you have the x, y, z, then you do computation of x and z, you get minus y.
What's xp? Now I've actually forgotten. Is xp minus I or px? I think that's the case.
Yeah, minus I, because if you do the right hand rule or left hand rule.
Yeah, I think so. I have a minus sign missing in my notes. Okay, so here's my point. I have the commutator. I've written the commutator of x and k, and it's equal to minus I. But I know for a fact, we've gone over this a couple times, commutator of x and p is IH. And what you get from this, sorry, I know I was rushing a bit. is that the K, the unknown operator, is actually P over H bar. And that's it. So there you go. Yeah, sorry, I'm holding you late, so run. That's all there is. You know what? This, in terms of like formal work, I think this is just tons of practice, but this is the translation operator. That's all you needed to know. I really just did this proof so you got some more practice with bras and cats and dx and I dx and all that jazz. That's all there is to it. Alrighty, alright, so next time, wait, what's that question?
You're missing the exam.
No, he got his exam. Yeah, you were late. Alright, and just tell you next time, so we're gonna, I don't really need to show you this. I could have just told you this is the translation operator. But again, it's just an opportunity to do some practice. But what we're gonna cover next time is, we're gonna cover this. And it's real similar proof that just goes on and makes a whole bunch of approximations. But anyway, so we're gonna do that next time and then drop it. But remember that when it comes to time, it's the exact same thing, but I can tell you, let me go ahead and preview. Instead of I1 minus I P, it's 1 minus I Hamiltonian. And that's the time evolution operator. So again, this is just a warm-up. Warm-up for that. This, you'll never see this again. I shouldn't be saying this over and over again. You'll never see this again. But you will see time. You will see that. Many times.